Okay, so here we are at chapter 6, which is all about lines and planes in space. And just so you know, some of you are going to have a hard time visualizing these three-dimensional shapes, but that's okay because you can still do all of these problems even if you can't see what other people see. Okay, you just have to go by what's given and really utilizing your definitions. Okay, so let's start us off. We're talking about relating lines to planes. So we need to define what a plane is. So a plane is a two-dimensional figure that has length and width, but no depth. So you can think of like the piece of paper that you're writing on. It can be considered a small plane, if you will, if you discount the thickness of the paper. And so when we go to draw what a plane is in a two-dimensional field, you're going to draw what looks like a parallelogram, just like this, and you're going to darken two consecutive sides so that it kind of gives it a 3D nature to it. And then when we go to name it, we're going to name it with a lowercase letter in one of the corners. So this is plane M. Okay. Now in your plane, you can draw all sorts of things. You can draw any of your lines and points and rays and triangles. So basically every shape that we've been able to draw, we've been drawing in a two-dimensional plane because you think of your paper as what you've been drawing it on. Okay, but what you do need to know is that planes go on forever and ever, infinitely, in both directions. So even though it's drawn to be finite, it does go on forever. So anything that is all in the same plane is going to be considered coplanar, so just like collinear. So all these points that we see down here, A, B, C, D, and G, these are all coplanar. And then the lines that you see, A, C, and D, B, these are coplanar lines because they're all lying in plane M. But maybe you see this point F that's hanging out above the line, and this point E that's hanging down, it's hanging out above the plane, and point E is hanging out below the plane. And you can tell that because the little dashed line here helps us visualize that we're seeing through the plane to this line going below it. So if we take all of these points that are in the plane and then include F or E, then we have non-coplanar points. And just the same thing, if we take both of these lines that were coplanar but then include line EF, those are non-coplanar lines. Okay? So there's some definitions for you. Here's another definition for you. The foot of a line. So if a line intersects a plane, it's going to kind of punch a hole through that plane, right? And that hole is probably pretty small. It's just a point. So when a line passes through a plane, the intersection is a point, and that point is called the foot of a line. So in this particular example, G, right here, is going to be the foot of line FE in plane M. Okay? All right, moving on. There are 4 different ways to determine a plane. And one of them is a postulate, and the other 3 are theorems based off of that postulate. So the first postulate that we need to talk about, which is really what we're going to come down to in every single situation, is that you have 3 non-collinear points, and they determine a plane. So you can see over here I have 3 non-collinear points, and they make this plane over here. So how do we get theorems 45, 46, and 47 from that postulate? Well, if you think about a line and a point not on the line, you would have 2 points on this line. There's actually an infinite number of points, but you can pick 2. And then this point that's not on the line, those are non-collinear points, so they make a plane. Same thing down here where you have 2 intersecting lines determine a plane. Well, you can pick 2 points on one line and then pick a third point that's not on the other line, but it is on this one. You would have a point here, a point here, and a point here. Then you have 3 non-collinear points. Same thing down here with the 2 parallel lines determine a plane. You can pick 2 points on one line and a third point that's on the other line. Those would be 3 non-collinear points. So what you're going to be asked to do is to actually prove one of these 3 theorems. And it's all going to come back to this postulate. And it is going to be a paragraph proof. And it's a little weird, it's a little different from what you're used to because they're not giving you givens and prove this and here's a diagram. You have to supply that yourself. So we're going to prove the first of those 3 theorems. A line and a point not on the line determine a plane. So the first thing that you're going to want to do is to draw a plane and draw what the situation is, a line and a point not on the line. So here's my diagram, and I've actually labeled point A, point B, and here's point C that's not on the line. So this is going to be a really quick, easy proof. It's only a couple sentences long. So the first sentence is that, given line AB and C not on line AB, we know that A, B, and C are non-collinear by the definition of non-collinear. Okay? So that's the first line. And you can adapt this for the other theorems, right? If it's two parallel lines, give them parallel lines AB and CD. Pick 3 points. Say that they're non-collinear by the definition of non-collinear. Okay. Once we have established that we have 3 non-collinear points, we go back to our postulate that says our postulate states that 3 non-collinear points determine a plane. Therefore, a line and a point not on the line determine a plane. So it kind of seems roundabout, but it is really basic. It's not too hard. Okay, so there's that proof. Next, we have a postulate that says if a line intersects a plane not containing it, so that means that this line cannot be drawn actually in the plane, it has to go through the plane, then the intersection is exactly 1 point, and we call that point, do you remember? It's the foot of the line. Okay. Next postulate, now this one's really hard, this is why I have these diagrams drawn for you. Imagine trying to draw that yourself. Postulate says that now if you have 2 planes, so plane N and plane M, and they intersect each other, their intersection is exactly 1 line. So you can see this pink line AB going through both planes. And so that's where they intersect. Okay? So you can kind of think about like when the floor, like think of M being the floor and N being a wall, that where the floor and the wall intersect is just this 1 line, which is like the corner on the bottom. Okay? Sorry. All right, so we're going to do a proof now. And you're going to notice that these proofs are very similar to proofs we did in Chapter 3. The only thing is that visually they're 3-dimensional. So they're going to be drawing these 3-dimensional shapes in a 2-dimensional space. And so they do some weird things to try to make it look 3D. So for example, these 2 triangles, PAB and PCB, are supposed to be sitting kind of at an angle with each other, but they're sitting on this plane. Okay, and so reading this, A, B, and C lie in plane M, notice that they didn't include point P. Well, that's so that people that can't see these 3-dimensional shapes know that P is above the plane. Okay, they tell us that PB and AB are perpendicular, so let's go ahead and mark that. And I know it doesn't look perpendicular, but they're doing that on purpose to try to give it a 3-dimensional feel. Okay, and they also tell us PB and BC are perpendicular. They tell us AB and BC are congruent. Okay, so those are congruent to each other. All right, so we're trying to prove that angle APB and angle CPB are congruent. So we have the givens. And then, since we had perpendicular lines, we had right angles by definition of perpendicular. We have right angles are congruent, all very straightforward things. We can use the reflexive property to talk about PB being congruent to itself. Okay. And so then we have side angle side, side angle side to say the 2 triangles are congruent, which allows us to use CP/CTC to prove what we wanted to prove. So if you look at just this proof, just all of these statements and reasons without even looking at the diagram, it looks like a proof straight out of Chapter 3. Really easy proof. Okay, so don't let the diagram hang you up and make it so you can't solve the problem, because it's probably pretty easy. Okay, so that's it for section 1. We only have one other section for chapter 6, so hopefully this isn't too bad. All right, talk to you later.